Hello everyone, welcome to this session, the first lecture for phase 2 in structural engineering. So today I'll be covering the topic influence line diagrams. In the last session or in the last lecture of the last session, I've already covered the influence line diagrams for beams, both determinate as well as indeterminate. So today I'll be covering the influence line diagram for trusses. Those who want to check, they can check the last lecture's recording available in NPTEL Gate portal. So today I'll be covering influence line diagrams for trusses. So what is an influence line diagram basically is? Can somebody confirm that whether I'm audible or not? One of you can confirm.
Yes, ma'am.
Okay, thank you so much. Yeah, so what is influence line diagram? So influence line diagrams represents the variation of either reaction, shear force, moments at a specified point in a member as the concentrated unit force moves over the member. So in simple language, we have to if we have to find the ILD for a particular member, what we will do, we will take a unit load or unit force and we will move the unit force along the length of the member and calculate the force in that particular member. Okay, we will if we want to do we want to draw the ILD for a particular member, we will move the unit force along the length of the member and calculate the force in that particular member. So in simple language, this is the ILD. Now, what is the difference between the bending moment diagram and the influence line diagram? The bending moment diagram represents the effect of fixed load at all the points. It represents the effect of fixed load at all the points, while the influence line diagram represents the effect of moving load at a point. So, in bending moment diagram, the load is fixed, but we are calculating the load at different points or at all the points. But it influence line diagram, that particular point is fixed or that particular member is fixed in which we have to determine the force, but we are moving the loads here. All right, in influence line diagram we are moving the loads, while in the bending moment diagram we have the fixed load and we are calculating the force at all the points. I hope it is clear. So this I have already discussed in the last lecture also. So two important things which you need to keep in mind regarding ILD is that ILD is straight line for statically determinate structures, while ILD is curved line for statically indeterminate structure. These 2 points will be very helpful while you are ruling out the wrong options in the gate problem. Please remember, ILD is always a straight line for statically determinate structure. You can note it down also. And ILD is curved line for statically indeterminate structure. So before trying a problem, you should see whether that beam is determinate or indeterminate, and in that way you can rule out the wrong options. For example, if for any particular structure, any particular determinate structure, if any option has a curved line in that IL in their ILD, then you can eliminate that option right away without even solving. Okay, so these few points you should keep in mind. This will help you in solving the problem very quickly, because your aim should be to get the right answer, to rule out the wrong options and to tick mark the right answer. Okay, so in gate, you'll not be given any marks for any steps. Okay, I hope it is clear. So this is a basic introduction of ILD. Now we'll start with solving gate problem of influence line diagrams for trusses. So it is gate CE 2007, question number 36. Okay, so we have to draw, so we have to find that this influence line diagram is given to us, the truss is given to us. We have to tell this influence line diagram belongs to which member. Okay, so four options are given to us, that the ILD is given. So this part of ILD is under compression and the rest of the part is under tension. Okay, so let us see if we could rule out some wrong options right away or not. Okay, so the members which are given to us are PQ, PS and RS. Okay, so we need to check which member has this ILD. So for this, let us consider a beam, for example. Okay, so let's consider this simply supported beam. whenever we apply a load on the beam, on the top of the beam, how will this beam deflect? It will deflect something like this. I hope you agree. If we apply a point load in the beam, it will deflect something like this. So the bottom members, the bottom surface will be under tension or compression. The bottom surface will always be under tension and the top surface will always be under compression. I hope you know this. So similarly in the truss, if we apply load at any point in truss, suppose at this point or any point in the truss, so it will deflect like, similar to the beam, it will deflect like this. I'm drawing the exaggerated version of this, but it will deflect something like this. Okay, so the top chord members will always be under compression. Like in the case of the beam, the top surface was always under compression. So in the truss also, the top chord members will always be under compression and the bottom chord members will always be under tension. So this point is important. How this point is important for our problem? So in our problem, our ILD which is given to us is varying. Some part is under compression while the other part is under tension. Okay, but we know that in a truss, the top chord member will always be under compression and the bottom chord member will always be under tension. So this can't be the ILD for member PQ, right? This can't be the ILD for member PQ. Why? Because if this would have been the ILD for member PQ, then it would always be under compression. It would have a shape something like this, always be under compression. Also, this can't be the ILD for member RS also, because if that would have been the ILD for member RS, then it would always be under tension because RS is a bottom chord member. So it would have the shape something like this. Okay, but in this case the ILD is varying. So we have ruled out the wrong options right away, that it can't be the ILD for member PQ and it can't be the ILD for member RS. Right? Now two options are left, whether it is for PS and or for QS, because this we can't say by simply looking at it. Okay, so before starting the problem, just look at the options first. If you could rule out some wrong options, then you have to you would require some lesser time to solve the problem. Okay, so we have ruled out our option number B and option number C. Now let's check. Now for proceeding further, we have to do some calculations here. Now let's check for member PS first. Okay, so how to draw the ILD for member PS? Okay, for this we have to, so from the definitions of ILD we have seen that we have to take a point load and we have to move the point load at different points in the truss. So we'll take a point load here and we'll move it from two different points along this line. Okay, so this we will do. Okay, so we'll take up we'll draw the ILD. We are drawing the ILD for member PS now, because other options, then we can check it for QS also. Okay, so we'll take a unit load and we'll apply it at this point first. Okay, starting from this point I have applied a unit load here. So whenever the unit load or whenever any load is applied at the support will take the entire load. Okay, if the load is applied at the support, you must be knowing that the support will take the entire load and there will be no force in any member. Okay, so if we are applying the load at this support, there will be no force in any member, so there will not be any force in member PS as well. Okay, so what we are basically doing, we are moving the concentrated load at different points and we are calculating the force in member PS. That is our target and that is the definition of ILD. Okay, I'll repeat again. We are moving the unit load at different points and we are calculating the force in member PS. Okay, so when we put the load at this support, let's call it as support A, then the support took the load entirely and there will be no force in any member and not in member PS. So the influence line diagram will be 0 here. Okay, now Similarly, for support, let's check for support, this support also. When we apply the unit load at this support, okay, so this support will entirely take all the load and there will be zero force in member PS. Okay, so these 2 points are clear. Okay, now we will check for other points. Now we will move the unit load at point R. Okay, we'll move the unit load at point R and we will calculate the force in member PS. Okay, now how to calculate this? So let us call this as A. All the spans, let's call them A. Okay, let's call them A. So how to calculate the reactions quickly? You must be knowing this, but I'll repeat again. So for let's call it as R1 and let's call it as R2. So R1 will be this length 1 multiplied by the other length other than this, so the length which is next to this unit load. Okay, so we are calculating R1. So 1 multiplied by this length, which is 4A, divided by the entire length. The entire length is 5A, right? So it is 5A. So this is a quick method for calculating the reactions here. Similarly, I'll calculate the reaction for R2 as well. So the reaction for R2 will be 1 multiplied by, why 1? Because we are applying unit load here. 1 multiplied by this length now. Okay, so the length after this unit load. Here also, for this support also we took this length, right? The length after that unit load. For this support, the length after the unit load is A, right? So 1 into A divided by entire length. The entire length is 5A. Okay, so this is a quick method to calculate the reactions. So we have, so this you can also use for beams. Okay, so we have calculated R1 and R2 now. Now we will calculate the force in member PS because that is our target. Okay, so for calculating the force in member PS, we will use the method of sections. Okay, very quick method. We'll just get to know because we are today we are going to solve a lot of problems similar to this. So even if you don't understand this one completely, then we'll do some more problems similar to this. Okay. Okay, so we'll use method of section to determine the force in member PS. Okay, we'll cut the section such that it will cut this member PS here. Okay, so I'll draw the section now. So it is recommended that we should take that section which does not contain this unit load. Okay, so I'll repeat again. So when we are cutting this section like this, so we have two parts now, right? Part 1 this and part 2 this. So we'll take that part which do not contain the unit load. So this part do not contain the unit load. So we'll take this. I'll draw this section. Okay. So I'll draw this section again. Please see to it carefully. This is force in member PQ. This is because we have cut those sections, so we have to draw the free body diagram like this. We have to release the forces here, FPS, and this is FRS, right? And we can draw the other section as well. So it is a complicated section kind of this, but we do not require to draw this, right? Because we can just make a dashed line like this. Like this. We do not bother about what is the orientation of the chords here. We do not bother about that right now. Okay, so this is we only draw the sections which we have cut. Okay, so and we have to draw this reaction as well, which is R2 and which is 1 by 5 here. Okay, I hope it is clear. Then what we will do, we will use a simple equilibrium equation, that is summation of force in vertical direction to be 0. This is a equilibrium equation we will use. So we'll use summation of force in vertical direction to be 0. And let's see what are all the forces in vertical direction. Please correct me if I'm wrong. I have the force R2 in vertical direction, right? I have force component of force FPS in vertical direction. Other than that, this is not in vertical direction. It does not have any component in vertical direction. this FRS also does not have any component in vertical direction. So the only two force are having components in vertical direction. Okay, so we will write those forces. So we'll write R2. R2 is upward, so let's consider upward as positive. R2 plus FPS is also in a vertical direction upwards. So plus FPS. What is the component of FPS in vertical direction? Sine theta, because we have considered this as theta. So FPS sine theta equal to 0. So FPS equal to minus R2 divided by sine theta. Okay, so what we got from here, we do not need to calculate the values here, because here we are asked just the shape of ILD, right? Because we are not given any values here, so just have to determine the shape of ILD. From here we get to know that force in FPS when the load is applied at point, which is at point R, when the unit load is applied at point R, the force in member FPS, the force in member PS is negative, that is in compression. Okay, so the shape, the ILD for this point will be, for the, let's consider this as A. For A point it is already 0, we know that, right? For member R, for this point we have compression. So downward I'll draw for compression and upward I'll draw for tension. Similarly, I'll calculate. Now I have calculated the force due to this point load at R. Okay. Now I'll move this point load to point S and then again calculate the force in member PS. Okay. So, yeah. So now I'll move it to point number S here. So I'll move it to S. Okay. This is A. This is A. So you do not need to calculate the reactions here, but let's just for practice, let's calculate. So R1 here will be this length, the length other next to the unit load, other than the unit load till the next support. So it is 1 into 3A divided by total length. So total length is 5A, right? And what is the reaction R2? The reaction R2 will be, the reaction R2 will be this length next to the load, which is 2A multiplied by 1 divided by the total length. The total length is 5A here. Okay, so we have calculated the reactions, although the reaction calculation is not required here, but just for the practice. Now, the same process. Again, we'll use the method of sections here. So we'll cut the member PS. So we'll cut that member in which we have to calculate the force. So we'll cut this member PS again. Okay, so what was recommended? It was recommended that we should take that section because it has divided this entire truss into two parts, these two parts. Okay, so we'll take that part which do not contain the unit load. So we'll take this part now, right? Because this section does not contain the unit load. Okay, so I'll draw this section. Okay, so we have cut this section like this, and I'll draw this section for you. Okay, so let's call it as FPQ. Okay, and this is FPS, which we have to calculate, and this is FRS, and this is the truss. Okay, and this is the force reaction R1. I hope it is clear. So if we'll cut it in this way, so this will be the force. So we have to release the forces for these three members now. I hope it is clear. Now again, the same thing. We have to just repeat the steps because just have to practice the steps. So again, we'll use the same thing, summation of force in vertical direction to be 0, right? Since we have considered this as theta, so this will also be theta, right? Now, summation of force in vertical direction. So what are all the forces in vertical direction? This is force R1, which is in vertical direction. This is not in vertical direction. This is not in, does not have any component in vertical direction. But this force FPS has, this is theta, right? So FPS sine component is in vertical direction, right? So we'll write all the forces. So R1 is upward, so I'm writing R1 as positive. and other than that fps sine theta, but it is in downward direction because its component will be in downward direction, right? Minus fps sine theta. Any other force in vertical direction? No, right? So it is 0 here. Okay, so we'll calculate fps as r1 divided by sine theta. Again, we do not need to calculate the values because we just have to know what is the shape of the ILT here. So when we applied the unit load at point S, we are getting force in FPS as positive, right? That is in tension. So we'll consider this as positive. So this here, somewhat above this line, somewhat above this baseline. So this is the shape. Now we can join the points. Okay, so I'll tell you just in a minute. So I'll join this and this and this. So this is the ILD for the member PS. Why I've simply joined it and not considered these all points? Because when we have to calculate the ILD for a diagonal member, only only the member, for example here we need to calculate it for member PS, so only there will be a variation between member R and S. Between these two sections there will be variation. Other than that it will be constant. It suppose at point S it is in tension, so till the support B it will remain in tension. Okay, so this is the case. We do not have to calculate it for all the points. We just have to chose those two sections which are joining the diagonal member. Okay, so suppose we need to calculate it for let's say, let's call it as mn. So we will put the unit load only at n. Okay, because putting at b will take all the forces and it will be 0 anyway. Okay, so whenever we are calculating it for calculating the ILD for diagonal member, we have to put the unit loads only at those 2 points which are only at those two sections which are joining the diagonal member. Other than that, it will, suppose it has come tension here, so it will remain tension till the end. Okay, and it has come compression here, so it will remain under compression till that support. So I hope it is clear. So we have already solved this problem. Okay, so what option it is matching with? So PS, yeah, it is matching with the ILD which is given to us. So the correct answer here is member PS. I hope it is clear. So for what we did, I'll just summarize it quickly. So before starting any question of ILD, if the ILD problem is related to beams, so please determine first that whether the beam is statically determinate or indeterminate. If it is statically determinate and some options contain the curved lines, you can just rule out that option then and there only. Okay, and if it is determinate, it will always be straight line for all the members. For influence line diagram of trusses, you can rule out the options that the top chord members will always be under compression and the bottom chord member will always be under tension. So, if so, this could not be an ILD for member PQ, and neither it could be an ILD for member RS. Only two options were available to us: member PS and member QS. Okay. So we try to take the first option, that is member PS. We try to draw the ILD for member PS and we get the answer. I hope it is clear. So this will save our time. Okay, I hope this question is clear to you. So I'll be solving a lot more questions similar to this so that this concept sink into your mind. Okay, yeah. So I'll solve another practice problem. So here we need to draw the influence line diagram for member GB. Okay, so for member GB, we need to draw the influence line diagram. So the first step is to calculate the reaction. So reaction calculation is only necessary where we need to know the values. For example, if there would be some values given to us, for example, 0.8 or 0.2, some values would have been given to us in different options, then only we need to calculate the reactions. Otherwise, it is not even necessary. So still, the first step is to calculate the reactions. Okay, let us draw this first. Different sections, let us divide it into different sections first. Yeah. Then the first step is to calculate the reaction. Just make it this way. So we'll calculate the reactions for different point load, different positions of point load. So the first position of point load will be A, right? But A is a support, so it will entirely take the load and there will be no force in member GB. So here it will be 0. Similarly for member E also, it will take the entire load and there will be no force in member GB. For middle points, we need to calculate. Now let's check for point number B. We'll apply the unit load at point B, right? We'll apply the unit load at point B, and after applying the unit load, we'll calculate the reactions. So let us call all the points as A again. It doesn't matter if they are different or same. Okay, so finally reaction won't matter here. So reaction R1 will be 1 multiplied by this length. So it is 3A divided by total length. Total length is 4A. Similarly, and the reaction 2, R2 will be 1 multiplied by this length, A, divided by the entire length, which is 4. So the reactions we have already calculated. Okay, so first step is completed. The calculation of reaction is done. The second step is to cut that section in which we need to find the force. So here we need to draw the ILD for member GB. So we will simply cut that section GB. So I'm cutting this section GB like this. The next step is to take that section which does not contain the unit load. So it has divided it into two sections. Let's say this is section A and this is section B. So it has divided it into two sections. So we will take section number B because it does not contain the unit load. Okay, so third step is to take that section. So let's do it here. So I've cut it like this. So I'm taking that section now, the section number B. So let's call it as F1. Instead of FGH, I'm calling it as F1. But this I'll call it as FGB only because we need to calculate this FGB. So naming is not important here. So let's call it as F2. Okay. Now, other than that, we do not need to draw any truss. You can simply draw the support here. So the support reaction was 1 by 4 here. Support reaction was 1 by 4. Okay, so second step is also done. First step is we have calculated the reaction. Second step is we have cut the section and we have drawn the section which is in the second part. Now the third step is to satisfy the vertical equilibrium. So the vertical equilibrium is summation of force in vertical direction to be 0. So what are all the forces in vertical direction? This one, 1 by 4. What else? FGB. Right, let's call it as theta, doesn't matter. So FGB, sine component of FGB, right? So 1 by 4 in upward direction, or I can write it as 0.25, 0.25, and FGB sine theta is in downward direction, so minus FGB sine theta, right, equal to no other force in vertical direction, so equal to 0. So FGB equal to 0.25 divided by sine theta. It is positive here. We just need to draw the shape here. So it is positive here, right? So when the unit load was at point B, it comes out to be positive. If you want, we are given the values of theta and A, then we can calculate the value also. But here it is not given, so we'll just draw the shape. So it was 0 here and it is positive here. Now we can similarly we will shift the load to point number C. For B we have already calculated. Now we'll draw for C. Yeah, let's do it here. Now we have shifted the load to point number C. Again, we will cut FGB only. So I'll cut FGB like this. Now I'll take the section which does not contain the unit load. Okay, so I'll make that section like this. I hope it is easy for you. It is, let's call it as F1. After cutting that section, I'm getting this kind of shape, right? It is FGB. Okay. and this is FBC, right? Now it is upward unit load, and the value of R, this RA we have calculated. So we'll again calculate it. So for this, it is at the middle, so it will be 0.5 and 0.5. Okay. So although it doesn't matter here, so we'll call it at R1 only. Next thing is, summation of force in vertical direction to be 0. Summation of force in vertical direction to be 0. So what are all the forces in vertical direction? We have R1. So R1, which is upward, so I'm taking it as positive. What other thing? We have FGB as well. So let's call it as theta. So sine component of FGB is also in the vertical direction. Other than that, no other force is in vertical direction. So plus, so FGB sine theta is also in upward direction. So I'm taking it as positive. So FGB sine theta equal to 0. So from that we get FGB equal to minus R1 divided by sine theta, right? So I'm getting this as negative. Okay, so when I've put the unit load at point C, I'm getting negative value. So as I have told earlier, for the inclined member or for the diagonal member, we will only move the unit load to 2 points, only to 2 points which are connecting that diagonal member. So 2 points are which are connecting the diagonal member are point B and section number C. Okay, so we do not need to calculate it for point D here. Okay, so let's join it. So we'll get the shape of ILD, this, this, and we do not need to calculate it for D. It will simply be like this. So this is the ILD for member GB. I hope it is clear. If anyone has a question, then they can ask. Otherwise, I'll continue with another question.
Ma'am,
Mm-hmm.
why do we calculate FD member, ma'am?
Why we are calculating it for FGB? You're asking?
Uh, no,
Uh-huh.
ma'am.
Huh.
Why
We,
can't we calculate FD member?
why are we not moving the unit load to point D? You are asking, right?
Yes, ma'am.
Huh,
Point D.
point D.
Point D.
Huh, we are not, because we can do that, but that is just a waste of time because we know that this will be somewhat lying here only. You can also do that. You can apply the unit load at D, calculate the reactions, cut the sections. You'll get somewhat here only, but that is just a waste of time. Okay, because it will anyhow come here only. You can check that also. Okay, just to
Non
save.
needed.
No need. It is not that we do not move. It's just that it's not needed. Okay. Right. So just we are saving our time here. So we are following the quickest method possible here. I hope it is clear now. A truss which is looking very complicated here, but you'll see it's very easy, similar to that we have done till now. Okay. Okay, so I'll you maybe you can try it on your own. Okay, I'll give you some time. At least you can rule out the wrong options. Okay, you can try to rule out the wrong options. So here it is a complicated looking truss. So we have to find the ILD for force in member U2 L3. It is also a diagonal member U2 L3. This member. So we need to find the shape of ILD for member U2 L3. Okay, so four options are given to us. At least you can rule out the wrong option here. Okay, so what is surely not the option? Can you tell me in the comments? Maybe some of you can try. Which is surely not the option. Which is surely wrong at this. Yeah, Nikesh has answered something. Yeah, yeah, it is right. We can rule out that option right here at this point only, because it is always in under tension. But the forces for diagonal member if it is in the middle, it will change from compression to tension, or from tension to compression, depending on the orientation of the diagonal member. Okay, so C cannot be an option here. Let us do it for member U2 L3. Maybe I want you to try it first. U2 L3. Okay, so there's less time, so maybe I'll do it myself only. So simple, very, very simple again. Okay. The first step is to, I can simply mark, at this point you must be knowing that I'll simply mark this point and this point as 0, right? Because when we apply the load at L1 and L7, it will entirely take the load. So because endpoints we have to mark. So if in any option, so you have ILD which has some shape like this, you can simply rule out then and there. Okay, because it cannot have the shape like this if the support is there, right? Yeah, so for endpoints I've already marked. Then the next step is to move the unit load at the only 2 points which are connecting that sections, okay, because that will be enough. So the two, we have to calculate the ILD for member U2 L3. So I'll move to point L2 and L3 only. I do not need to move it for the entire truss. Okay, just if it would have been given for U4 L5, then I would have the concentrated load only at L4 and L5. Okay, suppose I need to calculate it for U3 L4. So what should be the 2 points in which I have to consider the unit load? If I need to calculate it for U3 L4, can you tell me in the comments which 2 points should I consider? U3 L4.
L3, L4.
That is great. Okay, so this thing, yeah, good, very good. Let's make this session interactive so that uh, jage raho sab log. Okay, so I'll consider then after point L1, it is 0. It is 0 at L1, so I'll consider it at L2. So at L2, I've applied this unit load. Okay, now now what is the second thing? I'll calculate quickly the reactions. I don't need to calculate the reactions, but just see. Let's not calculate the reaction here. Okay, for this question, let's not calculate. I'll consider it as R2. But for sure, I know that R1 and R2 are going to be positive, right? Okay, because the load is applied in downward direction, so R1 and R2 are positive, and that is the only thing we require to know. Okay, so we have written it as R1 and R2. Now the second thing is to cut the section. So we need to calculate it for U2 and L3. So I've cut the section like this. Now I'll consider that section in which there is no unit load. So this section does not have any unit load, right? So I'll draw this section. Yeah, this, let's call it as F1, and this as FU2L3, and this as F2, let's say, because I do not need to calculate it, right? And other than that, there's a huge truss which I do not need to do anything with it. So I'll make it like a dashed line here. Then I'll make R2, right? So anybody would like to try what should be the value of F2, FU2, L3? I do not need the value exactly. I just need whether it is positive or negative. Everybody should try and write in the comment what value you are getting, it positive or negative. Yeah, Binoy has got negative. And what are others? What about others? Great. Rahul has also get negative. Ajas has also get negative. That's great. Means you are getting what we need to do. Okay. So after solving a lot of problems like this, what is the benefit of doing a lot of problems? The benefit is you are able to see the pattern in the problem. Okay. After doing a lot of problems, like for a diagonal members, you get to know that we need to calculate that the force will change only for L2 and L3 here. Okay, not for all the other members. So after a lot of practice, you will start to see the pattern in the problems, and in that way you'll be able to rule out the wrong options and take out the correct answer for it. Yeah, you were right. It is we'll do summation of force in vertical direction to be 0, and we will get Fu2 L3. Let's call it as theta, sine theta, plus R2 equal to 0, and we get the value of FU2 L3 as minus R2 divided by sine theta. See, we do not even need to find the reactions here. We just have to see the sign here, right? So I've got it as negative. Similarly, if I'll do it for member, so if I'll move the unit load to point L3 now, let's remove it from here and move it to L3. Okay, so some reaction will come R1 and R2. Let's name it as R1 and R2 only. Now we'll cut this section like this. We'll always cut this section in which we need to require the we need to calculate the force. We'll again cut the section U to L3, and what we will get, now we'll take that section which does not contain the unit load, just for the ease of calculation. There's nothing very technical about it. Okay, so it is FU2L3. Let's call it as F1 again, and it as F2 again. Okay, so it is like this, and this is R1, right? Now similarly, summation of force in vertical direction to be 0, and here R1 is in upward direction minus, because FU2L3 is in downward direction. Component of U2L3 is in downward direction. So minus FU2L3 sine theta equal to 0. R1 equal to, sorry, R1. FU2L3 equal to R1 divided by sine theta. So for your homework, you can check which orientation or which, because diagonals are either oriented in this direction or this direction, right? So you can check whether the orientation, how the orientation is affecting the answer. Okay, which orientation is giving, which is giving us the change from tension to compression, and which orientation is giving us the change from compression to tension. That, and if you could find some pattern there, then it will be very easy. You do not need to do this calculation also, right? You can simply see the options and take the correct answer. So getting to the point now, so Fu2L3 we are getting as positive here, so it is positive like this. So we can simply join the ILD now. It is here and here and here. So we got the answer like this simply. So or even though it is looking very very complicated, but it is very easy, you see, right? So which option it is matching? It is compression and tension here and compression here. So what is the option? Option number A. This is the answer. We do not need to calculate the values here. Okay. Okay. Now this question you can note down for your homework. Please either take a picture of it or just for practice. So in this question, they are asked when a load passes through Pratt type truss. Okay, Pratt truss. So this is one of the type of common type of trusses. So in this question, I think it was a gate question. I don't remember exactly, but in this question, this figure was not given. Okay, so if you do not know what a Pratt truss look like, then you could not solve the problem, right? So this figure was not given, so it is I recommend that you should know some common type of trusses. Just see what are the common type of trusses. So sometimes they might not give you the truss. Okay, so for this question they haven't given this figure, ki this is the Pratt truss or not. Okay, so please note down this question, and we'll discuss in the next session that what is the correct answer for this question. Okay. So now the truss part is almost completed. Then I want to take some problem from beams just for revision. Yeah, yeah. This is a problem of ILD from beam. So ILD for beam I have already discussed. Okay, but for this session I'll discuss. So if you want to know it in detail, you can check the previous recordings, right? Yeah. So here we are asked to find the ILD for member RA, RB, and RC. Just a quick question, whether this beam is determinate or indeterminate. Whether this beam is determinate or indeterminate. Because before starting that, you should know that. It will help you in selecting the correct option. Okay. Okay. So that's great. It's determinate. Okay. Why it is determinate? Just quickly we can see that. So this is simply supported and it is determinate. We know that, right? It is simply supported. This beam is simply supported and it is determinate. If we add one more restraint, it will become indeterminate by 1 degree, right? Because till now it was determinate, so degree of indeterminacy was 0 when it was simply supported. So I've added this support more, so it has become indeterminate by 1 degree. If I'll add one more support, it will become indeterminate by 2 degrees, right? So it is indeterminate by 2 degrees. Simply supported beam is determinate, and adding one more support will make it indeterminate by 1 degree. Now it is indeterminate by 1 degree. But if I'll add hinge here, it will release one restraint. Okay, so providing hinge will release one restraint. Okay, so it will again become determinate. If you want to solve it quickly, so it again become indeterminate, right? I hope it is clear. So this beam is, sorry, it again become determinate, right? So this beam is a determinate beam. Since it is a determinate beam, so the ILD for this beam will composed of straight lines, right? So in the last class, I've discussed the Muller-Breslau principle for calculating the ILD, for drawing the ILD, because that is a very quick method to draw the ILD for the beams. Now, how to draw the ILD of for member for RA using the Muller-Breslau principle. So for drawing the ILD for RA, what we will do, we will remove RA. That is, we will remove this vertical restraint. We will remove the vertical restraint. Okay, only the vertical restraint we will remove from point A. So we will remove this. Suppose this support is not at all here. This vertical restraint is not at all here. The second step is to apply the unit load or apply the unit displacement at point A. So if I'll take this point A and I'll move it upwards. Okay, I'll pick this point. Imagine a stick or a stick or a bar which is kept over the support like this, which has a hinge like this. Imagine it, and then I'll pick this part A and I'll push it upwards. So what will be the whatever will be the deflected shape will simply be the ILD for RA, right? So I'll pick that point A, that bar suppose, and I'll pull it upwards. So what is the shape? Please just check this is the shape or not. So I've this is one. I've displaced it by one amount. Now I've pulled it upwards. So this point B cannot move anywhere because it is supported at B. At point C, it also cannot move anywhere. Okay. Now if I'll pull it upwards, the shape would be, just you need to use some imagination here. The shape will be like this. Yeah. So this will be the shape, because at point, let's call it as point D, at point D there was a hinge, so it can rotate here, so it can have some relative angle change. Here this cannot have any angle change. If it is theta, so it has to be theta here, but it can have change in angle here. Now it is supported at here, so I'll join it simply like this. Okay, so it's a little complicated. If you want to see how that is the Muller-Breslau principle clearly, you should see my previous lecture. Okay, so I'll just draw it for simply supported beam, let's say first. Okay, let's say it's a simply supported beam. Just for revision, it is A and B, and I need to draw the ILD for reaction at A. So what I'll do, the first step is to remove the vertical restraint from point A. The second step is to pick this point A and displace it upward by unit amount. After displacing by unit amount, whatever will be the shape of whatever will be the deflected shape will be the ILD for RA. Okay, so here what will be the deflected shape? Deflected shape will be simply this, right? This will be the deflected shape. So this is the ILD for RA. So this is Muller-Breslau principle. I've discussed it properly in the last class. Now, the second thing is, so the second thing is we need to draw the ILD for reaction at B. So whenever we draw the ILD for reaction at B, same steps we need to follow. The first step is remove this support B, remove the support B and push it upward by unit amount. So imagine this bar, I'm removing this support B and I'm pulling it upward by unit amount. What is the shape? Whatever will be the shape of the deflected shape of the beam will be the ILD for this structure. ILD for RB, right? So it is supported here, it cannot move anywhere. It is supported here, it cannot move anywhere. From B, I have removed the support. Point D can move upward or downward. Okay. Now, if I'll pull it upwards, it will be displaced by unit amount here. So it is 1. So it will be like this. At D, there is an internal hinge, so it can change the angle and it will be like this. Okay, so I've discussed all these things in the last class, so you can check it. Just for revision, I'm taking the beam part also. Okay, so for drawing the ILD for reaction at A, you need to remove the restraint from that point and you have to pull it upward by unit amount. Okay, so I think that is enough for today's class. If you have any questions, you can ask me. And for this ILD for beams, for both determinate and indeterminate, you can check the last class recordings. Any question? Yeah, okay, that's good question. For RC, he's asking what is the ILD for RC? The similar steps we'll follow. We'll remove support at point C and we will pull this upward by unit amount. Okay, let's see what it cannot move anywhere from here. At A it is supported, at B it is supported, at D it can move. So I'm not putting it like any I'm not restraining it here. So but at point C, that Rahul is right, at point C we have pulled it upward, so it is displaced by one amount here and it will be like this. So when there is a hinge, just imagine a hinge here and everything else is supported and you are pulling it upward by unit amount, it will move like this, right? The bar will be like this and other points will be this. So this will simply be the ILD for RC. Okay, so it's very interesting. Like drawing ILD for beam is very very simple, and like if you got to know the concept once, then it is very simple to draw the ILD. Like 2 marks, because for ILD problems they usually ask for beams only, but whenever they ask for beams or whether for trusses, it will be surely a 2 mark question, and 2 marks like matters a lot. Okay, so if by simply remembering these few things, if you are getting 2 marks, it's very good, right? So Muller-Breslau principle has made the ILD thing very very simple. Okay, for trusses we have to do some little calculations, but for after practice you'll be able to see some pattern. uh, yeah, sure. Binoy, I have already discussed it in the last class. Shear and bending moment at any internal point in the past. I've already discussed this, but still, if you want any other session on ILD, then I can take another session maybe. So just if you can write in comments, because I've already taken this session. Okay, so I'll take next session for ILD problems only. Okay, I'll cover both indeterminate and determinate beam again, and we'll solve a lot of problems for IES and GATE as well, so that that concept sinks in. So that problems will be other than those I have covered in the last class. So that those problems will be different this time. So I can take another session on that next session. Maybe I'll keep it for ILD only. Okay, any other good thing? Okay, okay. So I think we have covered a lot. Please practice a lot, okay? Because that will help you only. Because structures problem require a lot of practice. You can't just mug it up. Okay, so okay, then thank you so much for listening. Okay, bye everyone. Okay, thank you, Dushyant. Okay, then bye.